All right, so what we're going to do is we're going to do the kinetic theory of gases here in this chapter. What this does is, okay, so we have a gas in this room. What all properties do you know about this gas?
It expands before the area.
Well, how do you characterize the gas? You tell its temperature, volume, pressure, okay? So a handful of variables. These are called thermodynamic variables, okay? Energy and so on. All right, and like we've said before, there are about 10 to the 28 molecules in this room, okay? And for all these guys, we just have a handful of uh, uh, parameters describing the state of the gas, okay? So what this chapter is about is the following. Let me show you a simulation here a second. Okay, so we'll fill this with gas. So what this simulation is showing you is the following. So here are these gases. It's at a temperature of 300 degrees Kelvin. The pressure is 35 atmospheres. Okay. And you can see that the gas particles are moving about. And what this is showing you the distribution of speeds. All gas particles are not moving at the same speed. So this is the distribution of speeds. We'll talk about this. This is the Maxwell-Boltzmann's distribution. There's the average speed of the gas molecule. What do you think will happen if I heat the gas?
Average speed will increase.
Yeah, the average speed will increase, okay? So notice the average speed. What is the average speed? 1200 meters per second. The temperature is 300 degree Kelvin. I'm going to heat it to 600 degree Kelvin. Hmm? All right, so we'll say that's 600 degree Kelvin. Okay. What's the average speed? Right. All right, so what you'll learn is the average energy per particle is proportional to the temperature. So when you double the temperature, the average energy has doubled. Okay? So the energy has doubled. What kind of energy does it have? Kinetic energy. So 1/2 mv squared doubled. So v squared doubled is this doubled. So the mass of the particles didn't change. V squared doubled. So v increased by a factor of √2. I hope you guys understood that. √2 is 1.4. And 1200 meters per second times 1.4 equal to 1700, right? So there you go, and that was the average speed. Okay. Why did the pressure increase?
Because the particles are hitting the walls of the container faster.
That's right. So they're hitting it harder, they're exerting a greater force, and the pressure increased. Okay. All that information is contained in the ideal gas law. Okay. So in the ideal gas law, what we'll assume is these particles are not interacting with each other except when they collide. Okay. So for instance, if there were charged particles, they would be attracting or repelling each other based on the charge. Okay. So this kinetic theory, this chapter assumes that they do not interact until they collide. When they collide with anything, the collision is an elastic collision. What does that mean, an elastic collision?
Anything so they're-
Energy is always conserved. Kinetic energy is conserved. Okay, so that's an elastic collision. Okay, so they do not, if they're far apart, they don't talk to each other. They only interact when they collide. The collisions are elastic collisions, and Newton's laws are obeyed. Okay.
So that means with an elastic collision, that means that the velocity just kind of it stays the same after the collision, it's just that reverse.
Okay, so for instance, pool, when you play pool, that's an elastic collision. So, and the masses are equal. What happens is if you have a head-on collision, the cue ball comes, and this guy goes with the same velocity. Okay, in the pool. All right, so in pool, those collisions are elastic collisions. Okay, so what this chapter is about is, based on those microscopic assumption, we are going to calculate the pressure of the gas, the temperature of the gas, and so on. Okay, so we are going to relate the microscopic properties to the macroscopic properties. That's what this chapter is about. Did you guys understand that? Can you see the gas molecules in this room? No. So we're going to tell you the average kinetic energy of the gas molecule is related to the temperature, which you can measure using a macroscopic instrument. Pretty neat. Okay, so that's what this chapter is about. You guys understand? Okay. All right. So we're going to go through all of these topics, but you guys can read all of this. Okay, what this diagram shows you is the following. This is a surface. Okay, so in a flask, in this flask, if you take a bunch of gas, that the state of that gas, or the state of the gas in this room, is a point on this surface. Okay. And now you do whatever you want to do to the gas. Heat it, or decrease the volume, increase the pressure, or whatever. All you're doing is moving around in this surface, as long as you do not change the number of particles. So for a given number of particles, no matter what you do to the gas, you're moving on this surface. Okay? If you take more particles, then that's a different surface. Okay? Each surface corresponds to the number of particles. Okay? So for instance, what will happen, let's see, what we'll do is we'll keep the volume constant, and we'll increase the temperature of the gas. Then you'll move along this line on the surface. Okay? If you keep the temperature constant and increase the volume, you'll move like this along the surface. Did you guys understand that? Okay. So if you keep the temperature constant, you'll be moving perpendicular to that axis. If you keep the volume constant, you're moving perpendicular to that axis. If you keep the pressure constant, you're moving perpendicular to that axis. Okay. All right, so you take an ideal gas. What is an ideal gas?
Gas with elastic collisions.
Glass with elastic collisions, and it's not interacting unless it's colliding and stuff like that, all the assumptions we made. Okay? And that's what we're going to talk about. So take a given amount of ideal gas, and it lies on this particular surface. Okay, now that's the modern view. Okay. Of course, this picture wasn't put together overnight. It took several years to put it together. You can see that it took 140 years to put this picture together. Okay. You guys today are born with the knowledge of the ideal gas law, right? You all have seen this 100 million times. Yeah. All right. Mr. Boyle, in 1662, discovered that the pressure and volume of a gas are inversely related when at constant temperature. Okay, so if you keep the temperature constant, this side is constant, and what he found was PV, the product PV will remain constant. Okay, so what Mr. Boyle found was constant divided by V. Okay, So temperature constant meaning if you keep you're only moving perpendicular to the temperature axis. So you're taking this slice, that slice of the surface. And that's what Mr. Boyle found. This is the curve he found in 1662. Okay. 120 years later, Mr. Charles found that constant pressure, so at constant pressure, what slice are you taking? A horizontal slice, right? At constant pressure. This is what Mr. Charles found. You raise the temperature and the volume increases linearly. At constant pressure, you raise the temperature, volume increases linearly. Okay. And Mr. Gay-Lussac found that when volume of the gas is held constant, so you're taking a slice perpendicular to the volume axis, and this is what he found. You raise the temperature, the pressure increases. Okay. And then finally in 1811, Mr. Avogadro found that the ratio of the volume V to N what does V to N mean? What are these? What is V? What is N? Number of particles, okay, is equal to KT over P. Okay, so is constant if pressure and temperature are kept constant. So if you keep the temperature and pressure constant, you double the volume of the gas. What has happened is you've taken double the number of molecules. You've doubled the number of molecules. Again, that's the only way to double the volume. All right, so there's the ideal gas law, and here's a modern perspective of it. Again, like I said, this was put together over a span of 160 years. Yep.
That's a K, right?
That's a K. A small K. Okay. So for a given amount of ideal gas, every state of the gas is a point on that surface. Okay. Here's the ideal gas law. So PV equal to NKT or PV equal to nRT. You see it in one of these forms. What is the difference? This is the number of molecules. This is the number of moles. That's the Boltzmann's constant. This is the gas constant. Okay. All right. So this is the number of moles. Okay, and R is the gas constant. Okay. And you guys know that at standard temperature and pressure, 1 mole of a gas at standard pressure is 1 atmosphere and standard temperature is 0 degrees Celsius or 273 degree Kelvin, occupies 22.4 liters, about 5.5 gallons, 5 to 6 gallons. Okay. There's the Boltzmann's constant. Okay. So that's the ideal gas law written in terms of Boltzmann's constant. Boltzmann's constant, the gas constant, and the Avogadro number are related like so. The Boltzmann's constant is gas constant divided by Avogadro's number, and it's 1.38 times 10 to the minus 23 joules per Kelvin. Okay, you'll be using that constant quite a bit. Okay. So again, how many gas molecules are there in this room? That is this number, N. There are about 10 to the 28 gas molecules in this room. Okay. What is the corresponding number of moles? About 10,000 moles. Okay. Okay, so these two numbers differ by a factor of the Avogadro number. They both differ by 10 to the power of 24, okay, which is the Avogadro number. All right, here's the Avogadro number that you have seen many times, 6 times 10 to the 23, or roughly 10 to the power of 24. Okay. What does this number mean? If you take 1 mole of any substance, that's how many particles of the substance you have. Okay. So if you take, here's how it's defined. If you take 12 grams of carbon, 12, their carbon, so that's the atomic mass of carbon, 12, okay? If you take 12 grams of carbon, you get that many carbon atoms, okay? So if you wanted this many water molecules, how much water do you have to take? So if you want this many water molecules, look up oxygen's atomic mass is 16, water is H2O. Okay, 16 plus 2, the hydrogen atomic mass of that. So if you take 18 grams of water, you'll have that many molecules of water. You'll have 1 mole of water and you'll have that, okay? So that's roughly a mouthful. Every time you take a gulp of water, you're gulping 10 to the 24 molecules of water. There, I just drank 10 to the 24 molecules of coffee, or mostly water. Yeah. Okay, so this is the ideal gas law. When is this true? Under the assumption that the molecules do not interact. Okay. Now, when the gas is dilute like this, like in this room, you can neglect their interaction. But let's say, I mean, you guys are all going to be high powerful engineers. You'll be dealing with very dense gases and stuff like that. And then when this thing doesn't work, you have to get a better formula, and this is a better formula for real gases. Now, if you're using this formula, then you made it. Okay. So if these gas molecules interact, if they attract, what happens? The pressure will be lower, right? Because they're interacting and they hit the walls at a lower speed. So because of if they have attractive interaction, the pressure gets reduced, and so there's the correction term. And what is this? This is the volume. What is relevant in this formula is the volume, the space for the molecules to run around it. Okay, so right now we put the volume of the room, okay, but you have to subtract the volume of the molecules themselves. But compared to the size of the room, that volume is negligible. But if you're dealing with extremely dense gases, then that might not be negligible. Okay, and so that's the correction term. Yeah. So this is the formula you would use in situations where the gas is very dense and it's interacting. Okay. So, for instance, you can't apply this formula for plasmas. Plasmas are ionized gases, and they strongly interact, so you can't apply this. Okay. Okay, so here's an interesting formula. Let's cool this gas down a little. Okay, and now what I'll do is so I've added this gas, another gas to it. Okay, what is the pressure? 48 atmospheres. That's a very large pressure. That's a large pressure. Now the question is, what fraction are the blue molecules contributing to this pressure, and what fraction are the red molecules contributing to the pressure? The blue molecules, notice they're bigger and heavier.
So they're
they're hitting the walls too, so they're contributing as well.
The red molecules are faster at hitting. They have higher average speed, so
Mhm.
therefore they're hitting the walls of the container more, which is increasing the pressure more.
Right. So all those. Okay. So what our friend said is, let's say you hit a ping pong ball and a golf ball. The golf ball is heavier, but the ping pong ball is moving faster and stuff like that. It turns out that Mr. Dalton figured this out. The partial pressure, the pressure contributed by each type of molecule is just equal to the fraction of the molecules. If the blue molecules are 10% of the total molecules, then they're contributing 10% of the pressure. That's what this statement says. Okay? So for instance, what is our atmosphere? 78% nitrogen and 21% oxygen, okay, and 1% rest of the stuff. So one atmosphere, 78% of the pressure is coming from nitrogen molecules, 21% from oxygen molecules, okay, and 1% from the rest. So that's what this formula is. Okay, did you guys understand that? And the total pressure is just the pressure due to each type of molecule. Okay. All right, what does this mean? Vapor pressure of water. That's the pressure due to the water molecules in the atmosphere. Okay? And this guy is important enough where you have the special tables. Okay, what does this table say? Saturated vapor pressure of water. What does that mean? Saturated vapor pressure. What do you think it might mean?
There's 100% humidity.
That's right. Okay, so when there's 100% humidity. So, the atmosphere at various temperatures can only hold so much water. Okay, and you can see as the temperature rises, the amount of water it can hold is increasing. So this is 10 to the 2. Okay, let's see, these are all 10 to 1.23. As the temperature is rising, the amount of water it can hold is rising. Okay, the temperature in this room, for instance, is 20 degrees Celsius right now. And the pressure of the water vapor, if it was 100% humidity, would be 2.33 times 10 to the 3 pascals, Newton per meter square. Okay, one atmosphere is 10 to the 5 pascals. Okay, so you see that this is equal to this number is equal to 0.023 into 10 to the 5 pascals. So at this temperature, if the humidity were 100%, the pressure due to water vapor would be 2%, 2.3%. You guys know what is the humidity in this room right now? It's more like 40 to 50%, 40%. Okay. Why is it 40%? That's what air conditioning does. Why do we do that? Okay, if the humidity is low, when you sweat, the sweat evaporates and cools your body. If the humidity was 100%, your sweat couldn't evaporate, and that would be uncomfortable. So you're spending a lot of money on keeping the humidity low, okay? And that's how you keep people comfortable, okay? So since humidity is 50%, the pressure contributed by humidity is about 1% in this room. The water vapor is contributing 1% of the pressure, okay? So this is a very important table, okay? And this also tells you when a fluid boils, when water boils, it's boiling, the pressure, all of the molecules here are water vapor molecules. So the pressure here is 1 atmosphere, okay? And so you can see that at 100 degrees Celsius, this is 1 atmosphere, okay? So if you find yourself on top of Mount Everest, water boils at 70 degrees Celsius, and the pressure would be 0.3 atmospheres. Okay, so when you're on top of Mount Everest, the air you're breathing is 30% that of at sea level. You'd better be fit. Either that or you have oxygen tanks. Okay? All right, so now we'll come to the kinetic theory of gases. So it's one of the goals on this chapter is to relate the macroscopic properties. What are the macroscopic properties?
Thermodynamic variables.
Yep. So they're called macroscopic properties because you're using macroscopic instruments to measure them, okay? Such as pressure and temperature in terms of microscopic properties of the gas. What are the microscopic properties of the gas? The mass of the gas, the kinetic energy of the gas, and so on. Okay? So we're going to relate those macroscopic properties to the microscopic properties that the gas molecules that you can't even see and stuff like that. Okay? We study ideal gases, so they're not interacting until they collide and so on. The collisions are elastic and so on. Okay, so they obey Newton's laws. The number of molecules is large. They undergo elastic collisions. Forces between molecules are negligible except during collisions. Okay? So that's the assumption. Okay. Is the space okay? You guys understanding this stuff? Okay. All right, so now we'll see how pressure arises. Okay. So you guys see that in this simulation, you see that molecules are bouncing off the walls and stuff like that. All right. So here we'll look at a particular molecule. So this will be our container. This will be our container, and this molecule is bouncing off this wall. Okay. The x-axis, you see the x-axis is pointing in this way. Okay. What is the change in momentum of the molecule? Okay, see the y component of the, we'll assume the y component of the velocity didn't change, only the x component of the velocity changed. Okay. So the change in momentum in for the x component, change in momentum is final momentum minus initial momentum. Okay, the final momentum is minus mvx there, minus initial momentum was mvx. So the change in momentum was 2 times m times the initial x component of the velocity. Okay. All right. Why did the momentum of the gas molecule change? Because the wall exerted a force on it. Okay. So the force exerted on the gas molecule was the change in momentum. Again, Newton's second law says the force is change in momentum divided by the time over which that change happened. Okay. Now this is one of the few derivations I will go over. Okay. So here's the change in momentum divided by the change in time over, divided by the time over which this happened. Okay, well, okay, so the molecule bounced off this thing, then it has to go to the other wall and come back. So it has to travel 2d distance before it gets to the next collision, again, on this wall. Okay. How long does it take? Well, 2d, that's the distance it has to travel. D is the dimension of the wall, divided by its velocity. Okay. So the force exerted on the gas molecule by the wall is that. And that's equal to the 2 cancels. It's mvx squared divided by d. Okay. The negative sign just tells you the direction of the force. And according to Newton's third law, if the wall exerted a force on the gas molecule in this direction, the gas molecule exerts a force on the wall in that direction. So the force on the wall due to single gas molecule is that. Of course, you saw that there's billions of gas molecules bouncing off. So you gotta add, so the total force on this wall, you have to add the forces exerted by all the gas molecules. Okay? And so that's what you're going to do. So the total force on the wall is the velocities of the n gas molecules that you have. Now, going back to that simulation, I'm not going to go to that simulation. Does the gas molecule prefer any direction? I'm sorry? No. So it'll be going, I mean, it goes in the x, y, and z velocities will all be equal. Okay, the average values. So this is what the sum of all this is, the number of gas molecules times the average x component of the velocity. That's the bar tells you the average divided by that. And the average x component of the velocity is just 1/3 the total velocity. Okay, so what we are saying is the x component of the velocity average is just 1/3 the average speed squared. Okay, and that's what that's written. Okay, so n is the number of gas molecules. This is the mass of each molecule, and we are relating that to the force. So that's, see, here's a microscopic property being related to a macroscopic property. Okay, so the pressure on the wall is the force on the wall divided by the area of the wall, force on the wall divided by d squared. Okay, and so this divided by d squared, n m v squared 3 divided by d squared, that makes it d cubed, and this is the volume of the chamber, this is the volume of the gas. Okay, and so that's 1/2, we write 1/2 mv squared, the 2 cancels, n divided by v, there's n divided by v, and there's the 3. All right, so this is your first big time expression. Let me go over this slowly. Okay, what is this? The average kinetic energy per molecule. Can you see a molecule? No. That's the average kinetic energy per molecule. That's being related to the pressure of the gas. Okay? You want to double the pressure, you have to double the kinetic energy per molecule. And this, what is this telling you? The density of molecule, number of molecules divided by the volume. Okay? You can increase the pressure by increasing the number of molecules. You can keep the average kinetic energy the same. Just if you want to double pressure, you can double the density of molecules as well. Okay? So this is a macroscopic variable and this is a microscopic variable. Okay? All right, so we've related the pressure to the average kinetic energy per molecule. Okay, and now we also, what we'll do is we'll use this, the ideal gas law, and relate this to temperature. Okay, so we'll equate this to that. Okay, so here's that formula, and here's the ideal gas law. So if you compare the two, what you find is the average kinetic energy is related to the temperature. So here is the second big time formula. And this is very important. Okay. We kept telling you that temperature measures how hot an object is. Now it's a more specific statement. This is a very precise statement. The temperature is related to the average kinetic energy per molecule. Okay. So here's an amazing thing. Okay, in a solid, the atoms are fixed. Okay, So what happens if you heat the solid? What happens to the atoms?
Start to move around. But they start to vibrate.
With a greater amplitude, right? Right now they're vibrating as well, so they'll vibrate with a greater amplitude. Okay. What's happening to these gas molecules in this room if you increase the temperature?
They move at a higher speed.
They move at a higher speed. Okay, now we derive this formula for ideal gas, but it applies to these as well. Okay, so the temperature gives you the average kinetic energy per molecule here and the average kinetic energy of these gas molecules. Okay, so the temperature of this table is the same as the temperature of the gas molecules. So the average kinetic energy of those gas molecules is the same as the average kinetic energy of the molecules of this table. Okay, kinetic energy. All right, so very important formula. All right, so here's the temperatures related to the average kinetic energy. Okay, now you'll come across this. What this is RMS velocity, root mean square velocity. Okay, it's sort of an average velocity. Okay, so here's where the name comes from, root. The bar is a mean, and that's the square. Okay, so there's the average kinetic energy, the average speed square. Okay, and you take the square root of that, you get the root mean square velocity. Again, like I said, it's sort of an average velocity, and that's an important quantity, so it's related to the gas temperature like this. It's 3 times the gas constant times the temperature of the gas. This is the molar mass. Okay, so if you want the mass of a single molecule, then you have to use the Boltzmann's constant. Okay, but again, this is a RMS speed of the molecule. So for instance, okay, at 20 degrees Celsius, here are the RMS speeds of molecules. Okay, 20 degrees Celsius is roughly the temperature of the atmosphere here. Okay, right now. Okay. What is the atmosphere of the Earth? What is that? What does our atmosphere contain? Yeah, what is it? So 78% nitrogen and 21% oxygen. Okay. How come we don't have hydrogen? 92% of the molecules in the universe are hydrogen. And we don't have any hydrogen. Well, it's in water, but our atmosphere doesn't have hydrogen. Okay, so it turns out that, so at this temperature, there's the RMS value. And if it turns out that, what is the escape velocity from Earth? 11 kilometers a second. And if the RMS value is about 1/6 the escape velocity, that molecule will escape. Okay. So knowing these RMS values, you can predict the composition of an atmosphere, if the gravity of the planet can hold that gas or not. That's why the escape velocity from the moon is much lower. It's about 2 kilometers a second, and all the gas escapes. So that kind of, this stuff is important for that kind of stuff. All right. Again, very important formula. The temperature gives you the average kinetic energy per molecule. Okay. Now here's a very important concept. It'll not come up in an exam, but you have to understand this. Equipartition of energy. Okay. So we just saw that the average kinetic energy per gas molecule is equal to 3/2 kT. What is that K? Boltzmann's constant. That's the temperature of the gas, and that temperature has to be in kelvins. Okay. All right, this guy is equal to that, 1/2 mVx squared plus Vy squared plus Vz squared. The 3/2 is 3 times half. Now, does the molecule prefer any direction? Does it like to go in the x-axis, y-axis?
No.
So this is the kinetic energy along the x-axis. This is the kinetic energy along the y-axis. This is the kinetic energy along the z-axis. So each degree of freedom contributes 1/2 kT. Okay. Each direction it can go in is a degree of freedom. Okay. So the equipartition of energy says when you dump a bunch of energy into a system, that energy is equally distributed among all degrees of freedom if they're accessible. Okay? It treats all degrees of freedom equally. Very important. Okay? Did you guys understand that? And that makes absolute sense, right? Now, of course, so it's like saying, if I have $100 and I can go to a bunch of restaurants, I am not partial to any restaurant. I'm just going to spend equal amounts of money. Now, if a dinner costs $500 at a restaurant, that's out of my reach, so I'm not going to go to that one, right? So any accessible degrees of freedom, the amount of energy spent on that is equally spent. Okay, very important. All right, you guys cool with me finishing this lecture? 10 more slides. Okay, I'll go a little over. We have 7 minutes left, but anyway, I'll speed it up. What do you think that means? Mean free path. Okay, here's the idea. Okay, so let's say, so our gas is mostly nitrogen. Okay, so the average speed of the gas molecules in this room is 500 meters per second. That's 1/2 kilometer a second. So the gas molecules are moving from here to Mainland High School in 1 second. That's how fast the gas molecules move. All right, so here's what I'm going to do. I'm going to take a perfume bottle. I'm going to spritz some perfume here. Yeah, I mean, the perfume molecules are a little heavier, but, so they travel a little slower. But it shouldn't take but a second to reach you. Less than a second. Will you smell the perfume in a second? No. Why not?
Because it's colliding with other particles.
So those molecules take the scenic route. Okay. So mean free path is the mean distance it travels before colliding. Okay. So for instance, here's an interesting fact. Okay. A photon created at the center of the sun takes 1 million years to get out of the sun. Why does it take 1 million years?
Because it's so dense and it has so many collisions with other particles.
It's talking to every electron and proton on the way there. Okay. Whereas a neutrino, also produced at the heart of the sun, a neutrino doesn't talk to anybody, and it comes right out within a fraction of a second. Okay? And that's how we know the core temperature of the sun. Okay? You can't measure the core temperature of the sun using photons because it's talked to everybody, and so you don't know the distribution. Anyway, so a neutrino takes 300,000 kilometers. Takes 2 seconds to get out of the sun, where the photon takes 1 million years. Okay? All right, so the mean free path is the distance between collisions. Okay. Typically, molecules collide 1 billion times per second. The average distance between collisions is the mean free path. Okay, now, the mean free path, okay, higher the density of molecule, what will happen to the mean free path? Will it be lower or higher? If you increase the density of molecules, what will happen to the mean free path?
It's
It'll be shorter because if there are more people, their chances of collision are higher. Okay? So mean free path is inversely proportional to the density of molecules. The larger the molecules, the shorter the mean free path. Okay, so and so the mean free path depends on the size of the molecules and the density of molecules. This is the frequency of collisions. That tells you how many times a particle will collide per second. Okay, so that's the frequency of collision. All right, so here are some numbers for the air in this room. And here's a good picture to have good numbers to remember. Okay, that is the size of the air molecules. Okay, remember this is 1/10 of a nanometer, 2/10 of a nanometer. Okay, this is the average distance between molecules. And notice this guy is 10 times that number. Okay, so if the molecules are the size of your fist, this is how far apart the gas molecules are. Okay, the mean free path is 100 times that. Okay, so if the size of the gas molecules are equal to your fist, they go about roughly the width of this room before they collide. Okay, a little more than that. And the gas molecules in this room are colliding about 1 billion times a second, 2 billion times a second. Okay. Okay, what is the average speed of the gas molecules in this room?
Half a kilometer per second.
That's right, 500 meters per second. Okay, half a kilometers per second. Is every molecule going at that speed? No. So this is the distribution of speeds. Okay, so some molecules are going at this speed. Okay, and here's the most probable speed. This is the most probable speed. This is the average speed, and this is the RMS speed that we talked about. Okay, so this is the molecular speed distribution, and this is called the Maxwell-Boltzmann's distribution, and it's given by this. So the probability of a molecule having this speed is given by that. So the distribution is v squared times e to the power of minus mv squared. So this is the kinetic energy divided by the Boltzmann's constant times temperature. Okay, so this is this was derived by Maxwell and Boltzmann, and so that's why it's called that distribution. Okay, so this is at a particular temperature. What do you think will happen if I heat the gas? What do you think will happen if I heat the gas? They'll move faster. Okay, and the distribution becomes like that, moves to the right. Okay, so there are more gas molecules moving faster. Okay, this gives you the number of molecules going at that speed. Yeah. All right, so here's so this is the curves calculated for 100,000 nitrogen molecules. This is the curve at 300 degree Kelvin and at 3 times the temperature. Okay, now this stuff is important. Okay, so for instance, here's this cup of coffee. Are water molecules escaping from this cup? Well, coffee is essentially water. Hmm? Okay, so here's a cup of water, and water molecules are always escaping. Okay, and it's these fast molecules that are escaping. Okay? Even at this temperature. Okay, so if the humidity is 100%, relative humidity is 100%, then there are water molecules coming in as well. If the humidity is 100%, then the number of molecules escaping is equal to the number of molecules coming in. What's that?
No, I'm thinking like if it's hot, like steam comes out, so it's escaping.
Okay. When the relative humidity is less than 100%, there are more molecules escaping than coming in. Okay, so that's why you want relative humidity to be less than 100%, so your sweat can evaporate. Okay, and these fast molecules are escaping. Yeah.
Does the distribution of the speeds of the different molecules continue to flatten out as the temperature increases until it reaches a uniform distribution
So when will it reach a uniform distribution?
at an incredibly high temperature?
At infinite temperature. Yeah. So what he asked, what our friend here asked is, when will this curve become flat at infinite temperature? Okay. All right, so this kind of stuff is important. So, okay, at all temperatures, gas molecules are escaping. Okay, so what is happening when gas molecules escape? The faster molecules are escaping. What's happening to the cup of water? It's cooling down because it's losing high energy molecules. So that's a great way to cool down something. Okay, you have a cup of water if you want to, and you know, in places where you can't afford air conditioning, what you do is you take a cloth, splash it with water, blow a fan on it. The water vapor evaporating will cool stuff down. Okay. All right. At the center of the sun, what is happening? 4 protons are combining to form a helium nucleus, right? And the mass of this guy is less, and so you get energy. Okay. Well, but these proton molecules repel each other. Why the heck are they combining? You know, you guys remember how close do they have to come before they can combine? 10 to the minus 15 meters. So only the fastest molecules, protons, can combine. Okay, so inside the sun, protons in the tails have enough velocity to overcome the repulsive force to undergo fusion. Okay. So if you want more fusion reaction to happen, what do you have to do? You have to increase the speeds, and so more massive stars have higher temperatures at their core, and they're burning faster, and they die faster. See, all that is contained in this curve. All right, again, these are VRMS speed, average speed, and most probable speed. Okay, so there are expressions for that. All right, so for solids and liquids, the way to measure the amount of solid or liquid is mass times the specific heat times the, you measure how much mass you have, how much of this stuff you have, okay, is measured using mass. Now when you have a gas, how much gas you have is measured conveniently in the number of moles of gas you have. Okay, so the amount of heat added to a gas is the number of moles, and this is the specific heat at constant volume times the temperature. This is the specific heat at constant pressure times the temperature. So this is heat added at constant pressure. Okay, now for a solid and liquid, it doesn't matter. The volume doesn't change, so you don't define that. But for a gas, the volume can change tremendously. Okay. So what this is showing you is, this is heat. So these are 2 isotherms. You'll learn isotherms are constant temperature curves. Okay, so you're heating a gas from this temperature to that temperature. Okay, this is heating at constant pressure. This is heating the gas at constant volume. Okay, when a gas expands, it does work. So the heat added during this process, the heat added during constant pressure process, this is heat added during constant volume process. You've added more heat during constant pressure process because you had to spend some energy to do work. You didn't do any work here. Okay, and again, we'll learn this in the next chapter as well. Okay. So this is greater than that. That means this is greater than that. Okay. So specific heat at constant pressure is greater than specific heat at constant volume. Okay. All right, we will give you an expression for heat, the specific heat at constant volume. So for an ideal gas, the internal energy of the gas is just the energy, kinetic energy of the gas molecule. So this is the kinetic energy of the gas molecule, and that's the number of molecules. So that's the energy of a gas. So in this room, the energy of a gas is just the average kinetic energy per molecule times the number of molecules. Okay? And so the internal energy, you can write it in terms of temperature to be that. The specific heat at constant volume is internal energy, d internal energy divided, okay, the rate of change of internal energy with temperature per mole. That's the specific heat. Okay, and you calculate that, and for a monoatomic gas, it turns out to be 3/2 R. Okay, all those guys, the noble gases, are all monoatomic, the last column of gases. Okay, so the specific heat for all of them is 3/2 R. Okay, and I had a table. Well, okay, I don't have a table anymore. Okay. So 3/2 R. Okay, so for all monoatomic gases, the CV is that. More complex molecules. So here is a monoatomic gas. This is helium. But if you have a diatomic gas like nitrogen and oxygen, okay. So at these temperatures, the molecule can travel in this direction. So that's 3 degrees of freedom. It can also rotate. Okay. Okay. So it can rotate about this axis. It can rotate like that, and it can rotate about this axis. Rotate like that. So how many degrees of freedom is that? Does this guy have? 5 degrees. This guy can go only to 3 restaurants. This guy can go to 5 restaurants. He's got 5 degrees of freedom. Okay. What is the total energy of the system? Now here's where each degree of freedom contributes 1/2 kT. If you have 5 degrees of freedom, that's how much energy you have. And if you have n molecules, that's the total energy of the system. So that's how easy it is to calculate. Okay. And you can calculate the specific heat, and it'll work out dt. It'll work out to F/2R. So if you have F degrees of freedom, the specific heat at constant volume works out to be that, F/2R. Okay, so what this is telling you is, see, this is amount of heat you need to add if you have n moles. So let's say that you have 1 mole and you raise the temperature by 1 degree Kelvin. That's the amount of heat you need to add. Okay. So let's keep this in mind. Okay. So here's a diatomic molecule. So this is a diatomic molecule with 5 degrees of freedom. Okay. So here's what this graph is showing you. Okay, so this is the graph for hydrogen. Well, okay, it doesn't say, but anyway, this is for hydrogen. And what is it showing you? CV for hydrogen. See, at these temperatures, CV is 3.5 R. So this is for a hydrogen molecule. CV, remember, is F/2R. F is the number of degrees of freedom. Okay, so at these temperatures, at 100 degree Kelvin, 0 to 100 degree Kelvin, the hydrogen molecule has only 3 degrees of freedom, meaning it cannot rotate. That restaurant is too expensive. At these temperatures, these are room temperatures here, the rotational degrees of freedom are in play. Okay, so the number of degrees of freedom is 5 degrees of freedom. This is the surface temperature of the sun. There are 2 additional degrees of freedom. The vibrational modes come into play. Okay, so they can vibrate as well. Okay, so you see, the richer you get, the more stuff you can buy. And the more energy it's needed to keep you happy. Okay, to raise the temperature by 1 degree Celsius, you need more energy, the more degrees of freedom there are. Okay, all right, so that's the kind of stuff that is useful to calculate when you do these. When more degrees of freedom come into play, you need more energy to raise the temperature of a substance. Okay, all right, we end